I delayed our second exam 1 week, so it is November 4th. November 4th would be our second midterm exam, and then we will have classes during the midterm exam period. So we have a class on 21st and we have a class 25th. I know in most of other classes they don't open the class during the midterm period, but we are behind our schedule. So I'll just do the class. And then we will of course have a quiz. And about second midterm exam, it will cover our class topics, the content we covered before midterm exam, and then remaining part of the Khan Academy, matrix transformation and alternative basis. 예. 10월 28일 수업이 있지. 뭐가 안 적혀있나? I'm sorry. 아, 그래요? 예, 없어요. 아, 그렇구나. 10월 28일 몇 빠졌지? 25, 28. 그렇구나. 잠깐만. Yes. Thank you for the information. 그러네. 그러면 그러네. 다 하나씩 옮겨야 되겠네. 또 빠진 거 없나? 11월 1일, 11월 4일. 시험 범위가 약간 늘어나겠네. 네. 예. 알려줘서 감사합니다. 이게 또 빠진 날이 18, 21, 25, 3 더하기 4, 3, 4. 더 안 된 것 같아요. 옮겨야지. 또 뭐야, 날짜가 왜? 22, 약간 22 다음에 18, 22, 22, 25, 11월 25일이 빠졌네. 또 다른 과목들은 어때요? 다른 과목들은 시험 그 주에 아예 과목 시험 수업이 없죠, 보통. 하루 시험 보고, 예? 근데 이제 보통 이틀로 나눠서 하는데 하루는 시험이면 하루는, 예? 그렇죠. 그냥 일주일 비워놓죠. 예, 그냥 우리는 일주일 수업합니다. 그냥 지금 공부 더 한다고 생각하시고. 재밌잖아, 이 수업. 그렇죠. 쉴 수 없지. 나와서 공부해야지. 퀴즈도 보고. 여긴 쪽지를 안 준비해왔네, 현시학생은. 자신이 있었구나. 뭐 나올지 알았어. 그렇지? 그냥 뭐, 공부하다 보면 뻔하잖아. 아이겐밸류로 시험 문제 낼 거라는 거. 아이겐밸류, 아이겐벡터 뭐 이런 걸로 시험 문제 낼 거라는 거 명확하지 뭐. 쪽지 준비해 올 것도 없지 뭐, 어떻게. 뭐, 열심히들, 잘하네. 뭐, 예. 그럭저럭, 예. 잘하네. 그렇죠? 잘들 하고 있습니다. 그냥 완벽하게 준비를 해왔군. 완벽하게 페이퍼를 준비해 왔어요. 네. 여기도. 네. 아, 이거 멋지다. 이거 잘 준비했을 때 내 강의 노트로 써야겠다. 강의들이. 그래서 틈틈이 퀴즈를 보는 게 장점이 있어요. 중간고사에 대한 부담이 없잖아. 사실 덜 하잖아. 틈틈이 공부하고 한두 개 망쳐도 되고. 여기서 그 교재를 산 사람, 텍스트북 산 사람 몇 명이나 돼요? 아, 안 샀구나, 제주로 한 명. 우리 교과서 거의 안 샀네. 이 문제는 중간고사 문제에 또 나올 수 있겠죠, 당연히. 네, 중간고사 범위 아이겐밸류, 아이겐벡터가 들어가니까 11월 4일 중간고사 문제 이런 문제는 시험에 나오기 좋은 문제잖아, 이런 문제가. 그렇죠? 아이겐밸류를 구하시오, 아이겐벡터를 구하시오, 다이애고널라이즈를 하시고 뭐 이런 건 중간고사에 나오기 좋은 문제고. So, do you need more time? 그러니까 답이 유니크한 건 아니에요. 아이겐 벡터를 그렇죠? 아이겐 벡터를 여러 가지 방법이 있으니까. 근데 뭐 어쨌든 아이겐 밸류는 유니크하죠. 이 정도면, so I think I gave you enough time. So why don't you collect your solutions? Thank you. The source of this problem is from this link. Yeah. So diagonalize. So diagonalize means that we transform a matrix into the diagonal matrix, and diagonal matrix looks like this, as you know. Diagonal terms are non-zero, and non-diagonal terms are zero. Actually, non-diagonal terms are zero, then it is diagonal matrix. So this matrix, 2, 0, 0, 3, this A matrix, this is diagonal matrix. Right? This is diagonal matrix. So, and then the eigenvalue of a diagonal matrix is just diagonal terms, right? The characteristic polynomials, determinants A minus lambda I, this is 0, it becomes characteristic polynomial of this matrix, right? So it is trivial that the diagonal terms are basically eigenvalue. Then what is eigenvectors? Eigenvectors are also straightforward in diagonal matrix. Eigenvectors are just 0, 1, 1, 0. Actually, it doesn't have to be 1, but if we want to normalize it, they are 1. So, well, for example, so we have two eigenvalue, 2 and 3, and when eigenvalue is 2, then eigenvector correspond to this vector. Basically, this vector is this column. This column is eigenvector. Eigenvector, and this is eigenvalue, and this is eigenvector for that eigenvalue, right? Because if we A minus 2I want to make it 0, and then this is 0, and then x2 means x2 is 0. x1 can be any number, right? x2 can be any number, right? No, x1 can be any number. As far as x2 is 0, any vector in which x2 is 0 is eigenvector, which means that the eigenvector is spanned by this one, 1, 0. So it is the normalized eigenvector. When eigenvalue is 3, as you know, then we can put 3 in the a minus 3i is 0, then it's minus 1, something like that, and then x1 is 0. So as far as x1 is 0, then it is eigenvector. And if we normalize it, it is 0, 1. So again, for diagonal matrix, eigenvalues are 2, 3. And then eigenvector for particular eigenvalue is just that column that including the eigenvalue, right? It's easy. So when it is the diagonal matrix, finding eigenvalue and eigenvector is trivial, very trivial. And then there is definition. So next, if we use a definition of the eigenvalue and eigenvector, so when we have A and let C is the eigenvector and D matrix eigenvalue, right? Eigenvalue, and then because this A V1 minus lambda V1, this is the definition of eigenvalue and eigenvector, so we can A multiplied by C is basically C multiplied by D, right? Again, in the C matrix, the column vector of C matrix is eigenvectors. And then for D matrix is a diagonal matrix in which diagonal terms are all eigenvalues, right? So by the definition of eigenvalue, eigenvector, we know AC, DC. No, AC equals CD. Well, then it is trivial. We can make it, we can diagonalize it. We can simply multiply inverse matrix of C in front of both sides. Then D equals C inverse AC. Right? D equals C inverse AC. And D is diagonal matrix. So we diagonalized A matrix into the D. So it is simple. You can if you diagonalize it, then the diagonal terms are simply eigenvalues. And then in order to diagonalize it, you have to pre-multiply a matrix and post-multiply a matrix, and that is the inverse matrix of the eigenvectors and then eigenvectors. And then matrix A is called diagonalizable. Matrix A is diagonalizable if there is an invertible matrix C. So as far as we can find this C inverse, so if C has inverse matrix, which C is a collection of eigenvectors, and if it has inverse matrix, then we can do this operation. So it is diagonalizable. Okay. The example, which is what was today's quiz, 260 minus 1. First, we have to find eigenvalues. Actually, for your quiz, you don't even have to calculate eigenvector, right? You can just calculate eigenvalue and just write down diagonal sum, that's the answer. But anyway, for step by step, first you have to find eigenvalues, and in order to find eigenvalue, you have to solve A minus lambda I equals 0. A minus lambda I is determinant of 2 minus lambda 6, 0 minus 1 minus lambda. And then we compute determinant of this one. But in fact, since it is the triangular matrix, actually this problem is very easy. It is the same to diagonal matrix. So actually eigenvalue is just diagonal term of this matrix. So the answer for today's quiz is you can just simply delete 6, then it is done, right? And that's the answer. 2, 0, 0, minus 1 is actually answer. Since it is upper, it is called upper triangular matrix. Upper triangle, upper triangle matrix. So we have numbers or only in upper triangle, it is 0. So for triangle matrix, determinant is just diagonal term. You know how to calculate determinant, right? And if you think about it, and if it looks like a triangular form, the matrix, the determinant is just a collection of multiplication of the eigenvalue are just the diagonal terms. So it is trivial. Yeah. So eigenvalue is 2 minus 1. You don't even have to calculate anything to solve this problem in some sense. But anyway, if we do this one, we can prove that indeed 2 and minus 1 is eigenvalues. And then because we computed eigenvalues, and then we can find eigenvector. Okay, so, well, by the definition of eigenvector, A, if V is eigenvector, then AV should be equal to lambda V, which means that A minus lambda I V is 0 here, it is X. So in order to find the eigenvectors corresponding to the eigenvalue lambda equal 2, then the solution of A minus 2I equals 0, and then looks like this one, right? A minus 2I x is 0, then it looks like this one, 0, 6, 0, minus 3, x1, x2, 0, 0. And if we solve this one, then it means x2 should be 0. x2 should be 0. Right? Then eigenvector is any vector in which x2 term is 0 and x1 is non-zero. Right? So it is eigenvector. So basically, eigenvector can be spanned by 0, 1, 0, 1, 0. Right? And 1, 0 is normalized term. And then eigenvector corresponding to eigenvalue minus 1 is, we can again plug this one. And then we solve this one, then it satisfies 3x1 plus 2, 6x2 equals 0. It means x1 is minus x2. So, well, when x2 is 1, x2 is minus 1, something like this. So therefore, this C matrix, which is a collection of eigenvector, is 1, 0, and minus 1. So if you pre-multiply inverse of this one to A and multiply this one after A, then it becomes diagonal matrix, which is 2, 0, 0, minus 1. So this is the process. Simple, easy. Any question? If we have Korean books for linear algebra, 선형대사, eigenvalue is 고유치, eigenvector is 고유벡터, 고유치, 고유벡터, right? 고유치, 고유치 문제, eigenvalue, 나무 위키, wow, 나무 위키, even 나무 위키 has, but this is hard to understand. It's not. So anyway, eigenvalue. Eigenvalue and eigenvectors. Again, the definition of eigenvalue is that this one. Lambda, if there is a V and lambda satisfy this relationship, then lambda is constant. Lambda is constant. So lambda is called eigenvalue and V is called eigenvector. And then, okay, so now we know mechanical way. Okay, so we know how to compute eigenvalue and eigenvector. Then question is, okay, what's the meaning of, why do we need eigenvalue and eigenvector? That is possibly one question. Let me answer easy question first. Eigenvalue and eigenvector has many applications. One simple application is like this one. One simple application is, well, yeah, this is another way of, history. Where do we use eigenvalue? Okay. Why do we need eigenvalue, eigenvector? If you ask Google, why do we need eigenvalue, eigenvectors? Well, yeah, for example, so we diagonalize this way. Right? So M is a matrix and D is a diagonal matrix. So we can express a matrix M into Q, D, Q inverse, right? We can express it this way. And suppose we are interested in the M to the power of N, right? Suppose we are interested in M to the power of 100. Well, that is maybe sound hard, but if we use this one, it is easy, right? Because M square, here look at this one, M square, we can express M square as QD, Q inverse, QD, Q inverse, then Q inverse Q cancels out. So M square is Q, D square, Q inverse. But D square is easy. D is diagonal matrix, so we can, we can square the diagonal. So it is easy. So likewise, M to the power of N, M to the power of N is, if we iterate this one, it is Q, Dn, and Q inverse. So we can easily calculate M. So suppose, where is the, so if there is M matrix, where is M matrix? M matrix is the, suppose M matrix looks like this one. We want to calculate N power of this M matrix, and then M can be decomposed this way. So M to the power of N is like this one, right? So 4 to the power of N, 2 to the power of N calculated into, so we can easily calculate M to the power of N. So this is one use of the diagonalization. And actually there is the simple one, and there are many other practical, many other practical application for eigenvalue and eigenvectors. In statistics, you will shortly learn in the second or third year, you will learn econometrics. For example, in econometrics, eigenvalue is important. And image processing, eigenvalue, eigenvector is important. Image processing. There are many applications for eigenvalue and eigenvector. Okay, so that's the why, that's the reason that we need to learn eigenvalue and eigenvector. Then next question is, well then, what is the geometrical interpretation of eigenvalue and eigenvector? What do they mean? What is the intuition of eigenvalue and eigenvector? There are very interesting interpretation of eigenvalue and eigenvector. And unfortunately, I found the YouTube video that explains this interpretation beautifully. So in the course web page, intuition of eigenvalue, eigenvectors, you can click this link, then you will reach this one. This is very fun. So it is 17 minutes, so let's just watch a couple of.
Eigenvectors and eigenvalues is one of those topics that a lot of students find particularly unintuitive. Questions like, why are we doing this? And what does this actually mean? Are too often left just floating away in an unanswered sea of computations. And as I've put out the videos of this series, a lot of you have commented about looking forward to visualizing this topic in particular. I suspect that the reason for this is not so much that eigenthings are particularly complicated or poorly explained. In fact, it's comparatively straightforward, and I think most books do a fine job explaining it. The issue is that it only really makes sense if you have a solid visual understanding from many of the topics that precede it. Most important here is that you know how to think about matrices as linear transformations. But you also need to be comfortable with things like determinants, linear systems of equations, and change of basis. Confusion about eigenstuffs usually has more to do with a shaky foundation in one of these topics than it does with eigenvectors and eigenvalues themselves. To start, consider some linear transformation in 2 dimensions, like the one shown here.
Okay,
it moves the basis vector I hat to the coordinates 3.
So suppose we have a 2 by 2 matrix, 2 by 2 plane, R2 plane, right? R2 plane. This plane, 2-dimensional space. And if we multiply 2 by 2 matrix, then this point will move to this point, right? If we multiply 2 by 2 matrix. So if we multiply a matrix to a vector, then it changes the location. Alternative interpretation is that, well, instead of changing the location of the point or vector, another interpretation is we change the space of this one, right? We change the space. We are slightly, to move this one to zero, we have to rotate this one, right? Rotate this one. So another interpretation of multiplying a matrix is first interpretation, changing the point, second interpretation, changing the space. Right? They are equivalent, right? So linear transformation is basically a special way of changing space. Rotation and stretching, basically linear transformation is stretching the space, right? Stretching and there are 3 operations. Stretching the space in the equal way, and another is rotation and flipping. Flipping is also possible. So these 3 operations is linear transformation of the space. Again, stretching and the rotation and the flipping. So this video is saying that. So yes, original space, and basically in this operation, we stretch and then rotate, something like that.
0 and j hat to 1, 2. So it's represented with a matrix whose columns are 3, 0, and 1, 2. Focus in on what it does to one particular vector, and think about the span of that vector, the line passing through its origin and its tip. Most vectors are going to get knocked off their span during the transformation.
You know what does it mean by spanning, right? Span. When we have 2 vectors, 2 independent vectors, 2 independent vectors, span plane, right? When we have one vector, it spans a line. Right? When you have 3 vectors, they are independent of each other, they span the space, 3D space, right? Nothing like this. They span.
I mean, it would seem pretty coincidental if the place where the vector landed also happened to be somewhere on that line. But some special vectors do remain on their own span, meaning the effect that the matrix has on such a vector.
Right? So we are changing the space in the linear scenario. We're changing space, so every vector to move the space, move the place. But some vectors, well, they may be stretched, but they don't move. They remain in the same line. Some vectors, they are eigenvectors. Okay? They are eigenvectors. So in some sense, eigenvalue matrix multiplication is the, again, stretching and then rotation of the line. So the line, so we can interpret linear transformation is that first we rotate line in the way of eigenvectors, in the we stretch by the amount of eigenvalue. That's the thing. So here we change the space, but this yellow line remains same. They are eigenvector, and then but they are stretched by some amount. That's eigenvalue. This is very important.
Is just to stretch it or squish it, like a scalar. For this specific example, the basis vector I hat is one such special vector. The span of I hat is the x-axis, and from the first column of the matrix, we can see that I hat moves over to 3 times itself, still on that x-axis.
So that's why x-axis is eigen.
What's more, because of the way linear transformations work, any other vector on the x-axis is also just stretched by a factor of 3, and hence remains on its own span.
That's eigenvalue.
A slightly sneakier vector that remains on its own span during this transformation is -1, 1. It ends up getting stretched by a factor of 2.
That's another eigenvector.
And again, linearity is going to imply that any other vector on the diagonal line spanned by this guy is just going to get stretched out by a factor of 2.
So multiplying this 3, 1, 0, 2 into a vector means that we are changing the space such that we are stretching this space into the x-axis by the amount of 3, and we stretch the plane by this way, -1 and 1 by the amount of 2. Then we have this transformation. So we know eigenvalue and eigenvector, we have more visual image, right? We have more correct way how we change the space.
And for this transformation, those are all the vectors with this special property of staying on their span. Those on the x-axis getting stretched out by a factor of 3, and those on this diagonal line getting stretched by a factor of 2. Any other vector is going to get rotated somewhat during the transformation, knocked off the line that it spans. As you might have guessed by now, these special vectors are called the eigenvectors of the transformation. And each eigenvector has associated with it what's called an eigenvalue, which is just the factor by which it's stretched or squished during the transformation. Of course, there's nothing special about stretching versus squishing, or the fact that these eigenvalues happen to be positive. In another example, you could have an eigenvector with eigenvalue -1/2, meaning that the vector gets flipped and squished by a factor of 1/2.
Okay, flipping now, because it's minus.
But the important part here is that it stays on the line that it spans out without getting rotated off of it. For a glimpse of why this might be a useful thing to think about, consider some three-dimensional rotation. If you can find an eigenvector for that rotation, a vector that remains on its own span, what you have found is the axis of rotation. And it's much easier to think about a 3D rotation in terms of some axis of rotation and an angle by which it's rotating, rather than thinking about the full 3x3 matrix associated with that transformation. In this case, by the way, the corresponding eigenvalue would have to be 1, since rotations never stretch or squish anything, so the length of the vector would remain the same. This pattern shows up a lot in linear algebra. With any linear transformation described by a matrix, you could understand what it's doing by reading off the columns of this matrix as the landing spots for basis vectors. But often, a better way to get at the heart of what the linear transformation actually does, less dependent on your particular coordinate system, is to find the eigenvectors and eigenvalues. I won't cover the full details on methods for computing eigenvectors and eigenvalues here, but I'll
So, again, eigenvalue, when we multiply a matrix, you can interpret eigenvalue, eigenvector such that eigenvector is the direction of the force, right? Direction of the force that changes the space, and eigenvalue is the amount of the force. So, well, in the statistics, this has large implication. We use eigenvalue, eigenvector given a data, right? If we have a data, we can find the most important variable in the data, like eigenvector, right? And the amount of that one. The importance of the particular variable is basically eigenvalue. So that's why it is important in statistics. And then image processing too. We can find the most important image, right? By this one.
try to give an overview of the computational ideas that are most important for a conceptual understanding. Symbolically, here's what the idea of an eigenvector looks like. A is the matrix representing some transformation, with V as the eigenvector, and lambda is a number, namely the corresponding eigenvalue. What this expression is saying is that the matrix vector product, A times V, gives the same result as just scaling the eigenvector V by some value lambda.
Right.
So finding the eigenvectors
Now
and
it
their
is clear
eigenvalue.
why we have this definition of eigenvalue, eigenvector. Right? Multiplying A to eigenvector, eigenvector doesn't move. right? Eigenvector is basically direction of the force. So if we multiply A matrix to eigenvector, eigenvector doesn't move. Just it is stretched by amount of lambda. That's why we have this particular relationship. That's why we have this. It doesn't move. It just stretches for the eigenvector because that is the direction of the force that changes the space. So now it is clear why we have this definition of eigenvalue and eigenvector. And then once we have this definition, then it is easy to find. It is now mechanical to find eigenvalue, eigenvector, just the way you did in today's quiz.
Of a matrix A comes down to finding the values of V and lambda that make this expression true. It's a little awkward to work with at first because that left-hand side represents matrix vector multiplication, but the right-hand side here is scalar vector multiplication. So let's start by rewriting that right-hand side as some kind of matrix vector multiplication, using a matrix which has the effect of scaling any vector by a factor of lambda.
That is the definition of eigenvalue and
The columns
eigenvector.
of such a matrix will represent what happens to each basis vector, and each basis vector is simply multiplied by lambda. So this matrix will have the number lambda down the diagonal, with zeros everywhere else. The common way to write this guy is to factor that lambda out and write it as lambda times I, where I is the identity matrix with ones down the diagonal. With both sides looking like matrix vector multiplication, we can subtract off that right-hand side and factor out the V. So what we now have is a new matrix, A minus lambda times the identity, and we're looking for a vector V such that this new matrix times V gives the zero vector. Now, this will always be true if V itself is the zero vector, but that's boring. What we want is a non-zero eigenvector. And if you watch chapter 5 and 6, you'll know that the only way it's possible for the product of a matrix with a non-zero vector to become zero is if the transformation associated with that matrix squishes space into a lower dimension. And that squishification corresponds to a zero determinant for the matrix.
So we are looking for a non-trivial V. If V is 0, 0, it is always satisfied. But we are looking for a vector that is not 0, 0. Well, if A minus lambda I is the non-singular, we can simply multiply inverse matrix of A minus lambda I. Then it means V is 0, 0. So that shouldn't happen. Okay? That doesn't happen only when A minus lambda I is singular matrix, which means its determinant is 0. Because its determinant is 0, it is singular, it means there is no inverse matrix. So we cannot multiply inverse matrix of A minus lambda each side.
To be concrete, let's say your matrix A has columns 2, 1, and 2, 3. And think about subtracting off a variable amount, lambda, from each diagonal entry. Now imagine tweaking lambda, turning a knob to change its value. As that value of lambda changes, the matrix itself changes, and so the determinant of the matrix changes. The goal here is to find a value of lambda that will make this determinant 0, meaning the tweaked transformation squishes space into a lower dimension.
Determinant is just
In this
area,
case, the sweet spot
area,
comes when lambda
Side of
equals
the area.
1. Of course, if we had chosen some other matrix, the eigenvalue might not necessarily be 1. The sweet spot might be hit at some other value of lambda. So this is kind of a lot, but let's unravel what this is saying. When lambda equals 1, the matrix A minus lambda times the identity squishes space onto a line. That means there's a non-zero vector V such that A minus lambda times the identity times V equals the zero vector. And remember, the reason we care about that is because it means A times V equals lambda times V, which you can read off as saying that the vector V is an eigenvector of A, staying on its own span during the transformation A. In this example, the corresponding eigenvalue is 1, so V would actually just stay fixed in place. Pause and ponder if you need to make sure that that line of reasoning feels good. This is the kind of thing I mentioned in the introduction. If you didn't have a solid grasp of determinants and why they relate to linear systems of equations having non-zero solutions, an expression like this would feel completely out of the blue. To see this in action, let's revisit the example from the start, with a matrix whose columns are 3, 0, and 1, 2. To find if a value lambda is an eigenvalue, subtract it from the diagonals of this matrix and compute the determinant. Doing this, we get a certain quadratic polynomial in lambda, 3 minus lambda times 2 minus lambda. Since lambda can only be an eigenvalue if this determinant happens to be 0, you can conclude that the only possible eigenvalues are lambda equals 2 and lambda equals 3. To figure out what the eigenvectors are that actually have one of these eigenvalues, say lambda equals 2, plug in that value of lambda to the matrix and then solve for which vectors this diagonally altered matrix sends to 0. If you computed this the way you would any other linear system, you'd see that the solutions are all the vectors on the diagonal line spanned by -1, 1. This corresponds to the fact that the unaltered matrix, 3, 0, 1, 2, has the effect of stretching all those vectors by a factor of 2. Now, a 2D transformation doesn't have to have eigenvectors. For example, consider a rotation by 90 degrees. This doesn't have any eigenvectors, since it rotates every vector off of its own span.
Yeah, some matrices doesn't.
If you actually try computing the eigenvalues of a rotation like this, notice what happens. Its matrix has columns 0, 1, and -1, 0. Subtract off lambda from the diagonal elements and look for when the determinant is 0. In this case, you get the polynomial lambda squared plus 1.
Right? In some case, it doesn't have a real number, real eigenvalues. Right? It means that every vector in the space is moved. Right? So it shows this example beautifully.
The only roots of that polynomial are the imaginary numbers, I and -I. The fact that there are no real number solutions indicates that there are no eigenvectors. Another pretty interesting example, worth holding in the back of your mind, is a shear. This fixes I hat in place and moves j hat 1 over, so its matrix has columns 1, 0, and 1, 1. All of the vectors on the x-axis are eigenvectors with eigenvalue 1, since they remain fixed in place. In fact, these are the only eigenvectors. When you subtract off lambda from the diagonals and compute the determinant, what you get is 1 minus lambda squared. And the only root of this expression is lambda equals 1. This lines up with what we see geometrically, that all of the eigenvectors have eigenvalue 1. Keep in mind, though, it's also possible to have just one eigenvalue, but with more than just a line full of eigenvectors. A simple example is a matrix that scales everything by 2. The only eigenvalue is 2, but every vector in the plane gets to be an eigenvector with that eigenvalue. Now is another good time to pause and ponder some of this before I move on to the last topic. I want to finish off here with the idea of an eigenbasis, which relies heavily on ideas from the last video. Take a look at what happens if our basis vectors just so happen to be eigenvectors. For example, maybe I hat is scaled by -1 and j hat is scaled by 2. Writing their new coordinates as the columns of a matrix, notice that those scalar multiples, -1 and 2, which are the eigenvalues of I hat and j hat, sit on the diagonal of our matrix, and every other entry is a 0. Anytime a matrix has zeros everywhere other than the diagonal, it's called, reasonably enough, a diagonal matrix. And the way to interpret this is that all the basis vectors are eigenvectors, with the diagonal entries of this matrix being their eigenvalues. There are a lot of things that make diagonal matrices much nicer to work with. One big one is that it's easier to compute what will happen if you multiply this matrix by itself a whole bunch of times. Since all one of these matrices does is scale each basis vector by some eigenvalue, applying that matrix many times, say 100 times, is just going to correspond to scaling each basis vector by the 100th power of the corresponding eigenvalue. In contrast, try computing the 100th power of a non-diagonal matrix. Really, try it for a moment. It's a nightmare. Of course, you'll rarely be so lucky as to have your basis vectors also be eigenvectors. But if your transformation has a lot of eigenvectors, like the one from the start of this video, enough so that you can choose a set that spans the full space, then you could change your coordinate system so that these eigenvectors are your basis vectors. I talked about change of basis last video, but I'll go through a super quick reminder here of how to express a transformation currently written in our coordinate system into a different system. Take the coordinates of the vectors that you want to use as a new basis, which in this case means our two eigenvectors, then make those coordinates the columns of a matrix, known as the change of basis matrix. When you sandwich the original transformation, putting the change of basis matrix on its right and the inverse of the change of basis matrix on its left, the result will be a matrix representing that same transformation but from the perspective of the new basis vector's coordinate system. The whole point of doing this with eigenvectors is that this new matrix is guaranteed to be diagonal, with its corresponding eigenvalues down that diagonal. This is because it represents working in a coordinate system where what happens to the basis vectors is that they get scaled during the transformation. A set of basis vectors which are also eigenvectors is called, again reasonably enough, an eigenbasis. So if, for example, you needed to compute the 100th power of this matrix, it would be much easier to change to an eigenbasis, compute the 100th power in that system, then convert back to our standard system. You can't do this with all transformations. A shear, for example, doesn't have enough eigenvectors to span the full space. But if you can find an eigenbasis, it makes matrix operations really lovely. For those of you willing to work through a pretty neat puzzle to see what this looks like in action and how it can be used to produce some surprising results, I'll leave up a prompt here on the screen.
It is the beauty of technology. If I want to explain everything with chalk and blackboard, it is a nightmare. But it explains everything visually with nice technology. I love it. Any questions about the yes? Eigenbasis. 길이값을 1로 만들면 편하겠죠. 뭐 굳이 안 해도 되는 거예요. 그 방향이니까. 근데 이제 보통 1로 바꾸죠. 그 베이시스도 오소노멀 베이시스로 만들고 싶으면, 그렇지? 오소노멀 베이시스, 뭐 배웠잖아. 오토노멀 베이시스로 만들고 싶으시면 그렇게 해야지. 꼭 그럴 필요 없는 거지. 뭐 단순히 백승한다, 뭐 이럴 땐 별 상관없는 거지. 이렇게 할 때. 근데 뭐 나중에 조작하기 편하고, 그러니까 코디네이트 시스템을, 그러니까 매트리스를 곱한 다음에 코디네이트 시스템을 바꾸는 거죠. 보다시피 코디네이트 시스템인데 나는 뭐 전부 다 이제 우리가 아는 XY는 0, 1, 1, 0으로 스팬된 거잖아요. 그래서 거기에 곱하기 몇 해서 2, 3은 지난번에 배웠듯이 2, 3은 2 곱하기 이렇게 하는 거 배웠잖아. 그렇죠? 근데 이제 코디네이트 오소노멀한 걸 쓰지 않으면 나는 다른 사람이 2로 쓰는 걸 1로 간주하겠다, 뭐 그런 의미니까 약간 헷갈리겠죠. 실질적으로 많이 오소노멀라이제이션을 합니다. 대부분. 그래야 조작이 쉬우니까. 헷갈리지 않고. 또 질문. Any other question? 그러면 오늘은 좀 yes. Today's question. Today's. Yes. So today is, you can find it in the this one. This one is the answer. So the answer is basically very simple. So today's quiz, the answer is the if you diagonalize A, you can simply delete 6. Then this is answer. 2, 0, 0, minus 1. And this is the process. Because this is 0. Okay, thank you and see you next Tuesday.